G'day and welcome to the first video for topic 3 for week 9. This topic is the kinetic theory of gases. So we've already talked about what we mean by a gas, how we think of temperature in terms of the motion of the particles of a gas. So this topic is extending that and starting to think about the kinetic energy of each individual particle and how that translates into a pressure. As usual, we'll jump over and we'll look through the slideshow and I'll see how we go. It probably will be a couple of videos plus the questions at the end, but we'll see how long it takes us. The goals for this topic, this lecture, are to state the assumptions of the ideal gas model, to explain the derivation of the ideal gas law. You don't necessarily need to remember or memorize how to do that derivation, but you should be able to understand the derivation. We want to be able to state the relationship between translational kinetic energy and temperature, describe and interpret the Maxwell distribution of speeds, and to define internal energy. So a few things to get through, and you'll notice they all sort of relate to the motion of gas particles itself. We already talked about some assumptions of the gas ideal gas model. We said that the particles had to be essentially a hard sphere, right? That they didn't have any other properties. We said they didn't have any internal degrees of freedom, which means no other ways to store energy, which is something we'll come back to later on. So they're essentially just a hard sphere, and any collision they do is perfectly elastic. And we've got some more points that we want to make, and that is that each particle moves in a random direction. So if you just have a gas chamber and it's full of gas, and you pause it and look at every single gas particle, all the directions will just be pointing in random, all the velocities will be pointing in random directions. Right, so if you take a snapshot, then there should be just a random distribution of velocities, whereas if you had all of them moving in the same direction, that's clearly not random, and that wouldn't fit the ideal gas model. There'd be something causing that, that distribution. The particles move with a variety of speeds. So again, we have random directions, and now we're saying that the magnitude of all those velocities is all different. So they're not all, or not all different, but there's a variety of them. They're not all exactly the same velocity. The third point is quite an important one. Particles are far apart from other particles. That means that they travel for quite a while before they bump into another one. Right? If they're bumping into each other really quickly, then we're actually closer to something like a liquid because they're all so close and dense. A gas obviously is less dense, so there's quite a lot of empty space from one particle to the next. The collisions between particles obey the laws of classical mechanics. The particles only interact through those collisions, so there's no electromagnetic forces attracting or repelling these particles. They just collide with each other, that's it, and those collisions are perfectly elastic. So that's the ideal gas model. There's quite a bit of assumption going on, but as I've said during some of my videos and Zoom sessions and things, these assumptions, you need to be aware of them, because if you are using these equations to calculate or to consider some scenario, you need to be able to stop and go, is this going to hold up? Right? We've made this assumption that the particles are far apart from other particles. Maybe you're designing a system, and at some point there's a compartment that's going to have gas in it, and you're assuming it's going to follow the ideal gas model, but it's actually going to have so much gas pumped into it that the particles get very close together, and you can no longer actually assume the ideal gas model will hold. And you need to be aware of that so that you can take that into account for your calculations and the design of that system. So understanding these limits of our model are very important. It's just as important as actually understanding the model itself. That said, let's take a really simple scenario and see what happens. See what happens when we consider the velocity of our really simple model, which is a single particle in a box. So we've got a little diagram of it there. We've got a box, area A on the end. The box is length L long, and we've got a single particle, and it's got some velocity in the x direction of Vx. We don't care about the velocity in the other directions. We're going to talk about them a bit later on. We'll come back and incorporate them, but for now we're only caring about the x component of the velocity. Importantly, that component can't change. What we'll do is we'll see that it'll be either positive or negative of that same component, but apart from that it can't change. There's nothing else to affect it, or I'll come back to that. It's less confusing in a moment. The question is, how can we determine the average pressure on the inside of the box due to this single particle? So this particle is flying around and it bounces off the walls of the inside of the box. And we know that pressure comes from the particles colliding with the inside of the container they're in. So if we know how fast this particle is traveling, if it's traveling with Vx in the x direction, can that tell us the pressure from this particle on that end of the box? And it can, and that's what we're going to try and do. So as I was just trying to say, when the particle collides with that end of the box, our velocity Vx, it was Vx, so positive x in that direction, bounces off the wall. That component, that x component, will now become negative x. Right? Now notice I've drawn it having shifted in the x or in the y or z directions. Excuse me. In the y or x directions, it doesn't matter what it's doing in the y or x directions. Right? Those are independent from its x component. So that means that we don't actually care what its y and x components are. They could be 0, they could be something else, they could be really high, it doesn't matter. All that matters, all that we're caring about is this x component. And the reason that's all we care about is because we're thinking about the area in this section, this end of the box, and we want to know the force applied to that end of the box by this particle. And when it collides with this, even if it does so at an angle, it's only the x component of its velocity that would change, the part perpendicular to the surface. And of course, that's the bit that we care about for the force, because the pressure is perpendicular. The force perpendicular to that area will give us that pressure. So we only care about that component. Even if the others aren't 0, we don't care yet. So when it does this, when it collides and turns around the other way, we know that its velocity has gone from Vx to minus Vx. So that means it's changed by 2 Vx. Right? It's gone from Vx to minus Vx. It's changed by 2 Vx. It's actually changed by negative 2 Vx, but we're going to just be very naughty and ignore that negative for a moment. So the change in momentum is equal to mass times the change in velocity, and that means we have change in momentum is 2 times mvx. And now think about how long it takes before it hits that wall again. So it hits this wall, it'll go off, it'll bounce off this wall, and then it'll hit this one again. Now we don't care about the collision on this end. I mean, it's relevant later on for the pressure, but at the moment we're only thinking about how quickly it will hit this one again, because this is the bit we're trying to calculate area for. And if it's some length L and it's got velocity minus Vx now, then the amount of time it'll take is simply 2L, it's got to go there and back again, divided by Vx. So that's how long it'll take between collisions. So every this many seconds, 2L over Vx seconds, it will hit this area A. And every time it hits that area A, it has this change in momentum. Right? And that means that the force from one particle on this, this end, now this is a time averaged force. So remember that the impulse is the change in momentum over change in time. What we're actually doing is using the change in time as being the time from one collision to the start of the next collision, right? And we're using the change in momentum as being the momentum that occurs right at that collision. So if you remember back to one of the tutorial or workshop problems where we talked about a ball hitting a wall, a tennis ball, I think it was, or it might have been in the mid-semester test even, the ball hitting the wall regularly, and we talked about the average force over time, then we had a bit of discussion about it in the workshop as well, following the test, I believe. And the idea was that it looked something like this. When the collision happened, right, you had a, so this is our time, and this is the force here. When the collision happened, you got a nice big spike. So we'll say that one happens right away at time t equals 0. You got a big spike in the force, but just for a moment, just for the duration of the collision. And then sometime later, right, we had another collision, the same big spike, but it was very short. And then nothing, and then nothing, and then another delta t later, we had another collision. Right? And so even though the force during the collision is really high, the average force over this whole time, if you zoom out and just see what the average force is, we don't have an average force all the way up here. because we've got this little peak of force here and then nothing for the rest of it. So the average is actually going to be somewhere around here. So that's our average force, right? Our average force is this smaller value here. And rather than calculate the force during the impact and then average it over that time in this derivation here, we're just going straight to the average. We're saying there's our impulse, our change in momentum there, and we'll divide it by that time between impacts, and that just gives us our average force over time for a single particle on this wall of our box. So if you are struggling with that concept of this time averaged force, spend a bit of time on it. That's perfectly fine to take a bit of time to think about it. If you want to go back and look at that previous question with about the balls bouncing on the wall, and go back to that and think about that, where you can actually calculate the magnitude of that force during the collision, and then see that over time it's a lesser amount of force. Feel free to go back. That's a good analogous example to what we're doing here. But for now, we're just going to go straight to this. So we have our time average force of one single particle on this area of the box. Remember, it does hit this one as well, but we don't care about that right now. We're just talking about this end of the box, is mv squared over L. So 2mv, and then we've got 2L over V on the bottom. So that Vx on the bottom goes up to the top. That's why we have Vx squared. So we have mass times square of velocity over the length, but the pressure is force over area. So we need to take that term we just got and divide it by the area. And that gives us area times length on the bottom, and the area times the length is just a volume. So that actually gives us that the pressure on this end of the box is the mass times the velocity x component squared, right, over the volume. So we have this term here, P equals mvx squared over volume. Now, just to be clear, this doesn't really make a lot of sense for a single particle. Right? So we wouldn't normally use this. It's just a good stepping stone to thinking about a gas with lots of particles in it, because obviously the amount of times it hits each wall will depend on what its velocity component is in each direction. So when we talk about pressure of a gas, we're talking about pressure in every direction, but for a single particle, the pressure that it applies to each inside wall of the box might be different. The two opposing ends will be the same, but the sides might be different. If it was just going back and forth, and if it didn't have any Vy or Vz, it would apply no pressure to the other sides, and that's obviously not what we expect from a gas. So it doesn't make sense for a single particle, but the maths is all valid. And the maths is valid when we move on to having lots of particles. I've drawn 5 in my box as an example, but there would be many particles in a box. If you remember back to the photograph of a balloon with helium in it, and it was 1 mole of helium, and 1 mole is 6.02 times 10 to the 23. So one balloon full of helium had 6.02 times 10 to the 23 helium particles, helium atoms in it. So that's the sort of number of particles we're talking about, not 5. But I'll use 5 for my illustration because I can actually draw that many. The force, the total force on this area of the box now is not just going to be the force from one particle bouncing and turning around, it's now going to be the force from all of the particles bouncing and turning around. So they're all, sorry, this mouse is terrible. We've still got the same mass for every particle. These gas particles are all identical, and they're obviously all still going over that distance. But now we've got the different velocity components, still all squared. We have v1x squared, v2x squared, and so on. They're all still squared, but we've got to add them all up to get our total force. And another way to write these, the sum of all of these velocities, if you imagine adding up all the squares of the velocities from v1 up to vn, all squared, and then divide them by n, that's our average of the square velocities, right? Velocity squared, and then average them. So that's another way that we could write it. We could multiply by n on both sides here. We would have n times this average square velocity is equal to the sum of all the squares. Right, so convince yourselves of that bit of math, and that means we can write our force due to some n particles of gas in a box is equal to m over L times n, the number of particles, times the average squared velocity. Now this step is hopefully nothing too difficult. You've all seen Pythagoras' theorem, where we have the square of two sides is equal to the square of the sum of the two squares is equal to the square of the hypotenuse. Now what we're doing is we're applying that to 3 dimensions, and just to convince you, I will take a moment to draw that. So if we've got our x, y, and z planes, that's a terrible graph, that should go straight through there, x, y, and z, and what we're doing is we're drawing in a triangle that goes out along the x-axis some amount, along the y-axis some amount, and then up the z-axis some amount, right? And this, we're saying that this is our velocity, right? That's our velocity. But what we've got is we've got a triangle on the bottom, and then once we know that, we know this length of that vertical triangle. So we're doing Pythagoras' theorem twice. Hopefully you're familiar with this, but just in case. So this is our Vx, this is our Vy, and this is our Vz. What I'm going to call this one here, right? I've drawn that a bit small almost. It's a bit hard to see what I'm doing now. But this line through here, once you take Vx and Vy, right, we'll call that Vxy, and that's the length of that line there. So Vxy squared is equal to Vx squared plus Vy squared. And now what we've got is we've got this triangle that's Vxy along the bottom, Vz up, and the actual V that we're looking for is the hypotenuse. So now we get that V squared is equal to Vxy squared plus Vz squared, but of course Vxy squared is just equal to Vx squared plus Vy squared. So this is just a little proof, barely a proof, but it's just to show you that the Pythagoras' theorem does work in 3 dimensions as well. So V squared is still equal to the sum of this 3 component squares, because they're all at right angles to each other. So if you're happy with that, then that means that our velocity vector, I'll jump back to the slideshow. Our velocity vector V squared is equal to the sum of all the components squared. Now, this is where one of our assumptions from our ideal gas model comes into play. What we said was that the velocities, if you freeze your system and look at all the velocity vectors, we said the directions are all random. The directions are all random. That means that the average in the x direction should equal the average in the y direction, which should equal the average in the z direction, right? Because it's random in every possible direction. So that means that overall, you could rename your x, y's, and z's any way you wanted, and they should always just be the same. It doesn't matter what direction you're looking in, because it was random, you should always just get that same average of the squares out. So that means that we can say Vx squared is equal to Vy squared equal to Vz squared. Again, all the averages there. And that means that the average of your velocity squared is equal to 3 times the average of your x component squared. And that means we can rewrite our force equation. So just going back a slide, we've got the force is equal to m over L times n times the average of the x component squared. But we just said the average of the x component squared is equal to 1/3 of the velocity squared average. So we can put that in. We put 1/3 in and we replace Vx squared average with V squared average, and we get that equation out. So now we've got the force from n particles being given by that equation. So we're no longer caring just about the x component, we're now caring about the velocity overall. And of course, that's perfectly fine, because when we're talking about a pressure, as I already said, gas exerts pressure in every direction on all surfaces equally. So it makes sense that we can generalize to the velocity in general, the total velocity, rather than just looking at one component or another. So it makes perfect sense that we're doing this. Now that we've got a force, we can go back and turn that into a pressure. And again, we just divide by our area. Just as we saw for a single particle, that then becomes a volume on the bottom. So we get 1/3 times the number of particles times the mass times the average of the square velocities divided by the volume is equal to the pressure. Or if we multiply through by volume, we get PV equals 1/3 Nm times v squared average. And hopefully you've stopped and said to yourself, that looks familiar, right? Because if we compare it with the ideal gas law, PV equals NKT, we can see that we've got, both of them have PV on the left, they've both got an N on the right, and so that means that the KT on the right in our ideal gas law must be equal to the third MV V squared average on the right of our derivation. And so that's the last equation there. KT is equal to a third times the mass times the average of the square velocities. So what's that telling us? Hopefully you're thinking that the right-hand side of that looks kind of like kinetic energy. Half mv squared, a third mv squared, it's similar, right? So what we can do is turn it into one, turn it into kinetic energy. But because we've got a third and we need a half, what we do is we just bring in this extra factor. We multiply by 2/2, but then we write it as 2/3 times a half. So that's still equal to a third. A half of 2/3 is 1/3. So we haven't changed the equation. We've just written it this way so that we can separate the half and the 2/3. And we get KT is equal to 2/3 times the average kinetic energy. So the average kinetic energy of all of those gas particles, if you get that average kinetic energy, 2/3 of that is equal to K times T. Remember, K is our constant and T is our temperature. So moving that 2/3 over the other side, so divide by 2 times by 3 on both sides, we get that the average kinetic energy is 3/2, 3/2, times the Boltzmann constant times temperature. And that should be, again, no surprise, because we've already said this several times. We've hopefully drilling home this concept that temperature is kinetic energy. That's what it is. Temperature is the translational kinetic energy of the particles in the object. So for a gas, that kinetic energy is just them flying around. So it's literally just standard kinetic energy, like we saw when we talked about energies the first time with our basic simplified systems. So hopefully nothing surprising, but what was interesting is that we actually proved it. We started just by saying, if this particle has this velocity, and we ended up with that ideal gas law. So that's quite interesting, that derivation, and it just gives us a way that we can actually define temperature in terms of kinetic energy, or vice versa. If we know the temperature, we can calculate the kinetic energies of all the particles. So a note here that we can't measure the velocity of every individual particle. It's not possible for us to actually freeze a system and look at every single gas particle and measure their velocities. Can't happen. But what we can do is measure the temperature, use this relationship to figure out the average kinetic energy. And from that, we can do some statistical analyses and actually look at the spread of velocity, spread of kinetic energies, and all of this. We're going to start to touch on some of this, but we won't get too complicated. So it's a very useful starting point to have this equation where we can say, here's our average kinetic energy of all of these particles. But we can never go all the way down and say, here's this one individual particle, here's this other individual particle, and look at their specific velocities and kinetic energy for every single particle in a box of gas. We just can't do that, right? Not practicable. It turns out that this equation, even though we got there by saying, let's consider an ideal gas, right? And I made a big deal out of saying that when we make all these assumptions about an ideal gas, we have to be aware of where these assumptions stop, where they break down, and we can't assume what we've done is correct anymore. But it actually turns out that the result we just got, the kinetic energy is equal to 3/2 kT, that result actually holds pretty well for liquids and solids, not just gases. So most substances do abide by this equation, but there is some other relevant factors that complicate things for some of the other things, some of the other aspects of the system we talk about. So the ideal gas law obviously won't hold for a gas or for a liquid or a solid, but the average kinetic energy part, that one conclusion that we came, this one equation that we got out, that does actually hold pretty well. Another thing that's worth just being really clear about is that we've been talking about the average of the square velocities, right? And the average of the square velocities is not the same as the square of the average velocity, right? Those are two different statements. because one of them you're squaring all the velocities on their own and then averaging them. The other one, you're averaging all the velocities first and then squaring that average result that you get out. So it's a very big difference. Actually, there's a question that I'll ask in a moment, so I'll stop talking about that right now. What we do is we define the square root of our average, of our squared velocity average. The language around saying these gets a bit messy, which is why we write them, right? So the square velocity average, when you take the square root of that, we call that VRMS. And given our definition for the average of the square velocities, we can see that VRMS is equal to the square root of 3 kT over m. You may have met RMS before. It means root mean square, right? And that's because we take the square root of the mean of the squares. So it's just root mean square is the description of how we got the term, got the result. And you may have met that before if you've looked at AC circuitry or electronics before, and they use a similar function defining voltages. So you may be familiar with that already. But regardless, just that's what RMS means, root mean square. Now, there's a little discussion here just to really drill home this point. We were talking about the average of the square velocities. What would be the actual average of the velocities? Right? So we said, I'll go back a slide, we said that the average of the square velocities is not the same as the square of the averages, but what is the actual average of the velocities in an ideal gas? So I do expect you to think about this for a moment. I'm going to obviously give you the answer and talk it through in a moment, but do think about it, try and answer for yourself first. Hopefully that's enough rambling on my part for you to have had a go at it, and let's go on. The average velocity will be 0. Right, so this comes back to our assumption again. Remember that we said for an ideal gas, if you freeze frame it, the velocities are all pointing in random directions. And therefore, for every direction that you've got a velocity going, you'll have one going the opposite direction. So they're all going to average out. They're all going to cancel out. You'll end up with 0 average component in each direction. So our average velocity is actually 0. So what we've got is this VRMS is definitely not 0, right? KT over m, that's definitely giving us an actual value for our average, for our root mean square velocity. But if you squared the average velocity, you'd actually be getting 0. You'd be squaring 0. So root mean square velocity is a useful value. Average velocity is 0, which is not useful, doesn't tell us anything about the system. From now on, we're not going to be talking about velocities, we're going to be talking about speeds. So we're not caring about the direction, we're caring about the speed of each particle. We still write it as v, but just be aware that at this point we're talking about speeds at scalar. And worth also mentioning, the average speed is not 0. The average velocity was 0 because the directions are all cancelled out, but the average speed is not 0, but it's still not equal to the root mean square velocity. It's still different, okay? If you really want to convince yourselves of that, you can Google it, or you can just do it yourself. Try doing the square of the average of 3 random numbers, and then do the root mean square of those numbers, and just look at what you get, right? So just play around with it. If you really need to convince yourself, I think the textbook may give you an example where it talks through squaring the averages and then versus averaging the squares. But yeah, just do investigate that if you're still not convinced. So actually, we'll stop there. I'll make a second video for the next half. So that's the first part. Is we got out this average velocity, this RMS velocity. So in the next video, we'll pick back up from here and we'll talk about the distribution of speeds.